practice of bonding the grounded conductors of multiple transformers together can create several electrical issues, primarily centered around National Electrical Code compliance, safety, and performance. NEC Section 450.14g explicitly states that the grounded conductor, commonly referred to as the neutral, of a multiphase system should not be grounded at more than one single point. This is a critical requirement designed to prevent circulating currents and ensure proper operation of the electrical system. In addition to this, NEC Section 250.24d mandates the use of separate neutral and grounding conductors throughout the entire wiring system. This separation is essential for maintaining a dedicated path for fault currents, enhancing safety, and minimizing the risk of electrical shock. Reinforcing these requirements, NEC Section 250.26 further prohibits the bonding of neutral and grounding conductors at more than one location within a building or structure. Multiple bonding points can lead to unintended current flow through the grounding system, potentially causing interference with sensitive electronic equipment and increasing the risk of electrical hazards. Beyond the specific NEC references, expert opinions from electrical engineering professors highlight the importance of adhering to these codes. Dr. Frederick Hartwell, an electrical engineering professor, asserts that the practice of bonding the grounded conductor to the frame of a transformer is unacceptable and directly violates NEC rules. He emphasizes the need for a single, well-defined grounding point to ensure proper system operation. Similarly, Professor John Danner, another electrical engineering expert, emphasizes that the grounded conductor should only be bonded to the frame of the transformer at a single point. This single point bonding prevents the creation of ground loops and minimizes the risk of circulating currents. The concerns surrounding multiple neutral bonding points are further supported by factual observations related to electrical system behavior. One key issue is the potential for unbalanced current flow. When the grounded conductors of multiple transformers are bonded together, it can lead to unequal distribution of neutral current. This can result in overloading of the neutral conductor in certain segments of the system and overheating of the transformer itself, potentially leading to premature failure. In addition to unbalanced currents, the practice of multiple neutral bonding points can also create ground loops. Ground loops occur when there are multiple paths for current to flow to ground, creating a closed circuit. These loops can act as antennas, picking up electromagnetic interference and injecting noise into the electrical system. This noise can disrupt the operation of sensitive electronic equipment, leading to malfunctions and inaccurate readings. Furthermore, ground loops can create a pathway for stray currents to flow, increasing the risk of electrical shock and potentially damaging equipment. Another critical aspect to consider is the importance of underwriters' laboratories, or UL, certification. UL certification ensures that a transformer has undergone rigorous testing and meets specific safety and performance standards. These standards are designed to protect against various electrical hazards, including overcurrent, overvoltage, and insulation breakdown. Transformers that are not UL certified may not provide adequate protection against these hazards, increasing the risk of electrical fires, equipment damage, and personal injury. It is vital to use UL certified transformers to ensure compliance with safety regulations and to minimize the risk of electrical hazards. When evaluating whether to replace C-rated transformers with UL certified units and separate the neutral conductors, consider the following points. Firstly, the existing configuration violates NEC codes 450.14, G 250.24, D, and 250.26, F5. These violations expose the installation to potential safety hazards and code compliance issues. Secondly, multiple bonding points create the risk of unbalanced current flow, potentially overloading the neutral conductor and causing transformer overheating. Thirdly, ground loops introduced by multiple bonding points can disrupt sensitive electronic equipment and increase the risk of electrical shock. Fourthly, C-rated transformers may not meet the same stringent safety and performance standards as UL-certified units, increasing the risk of electrical hazards. Fifthly, replacing the transformers and separating the neutrals provides a safer, code-compliant installation, reducing the risk of electrical hazards and equipment malfunctions. In summary, adhering to NEC guidelines, separating neutral conductors, and utilizing UL-certified transformers are paramount for ensuring a safe and reliable electrical system. Ignoring these principles can lead to code violations, equipment malfunctions, and increased safety risks. It is highly recommended to replace the existing C-rated transformers with UL-certified units and implement a separate neutral and grounding conductor system to mitigate these potential problems. Understanding these principles and their application is fundamental for anyone working with electrical systems. Let's delve deeper into the specific code references and their implications. NEC Section 450.14g, as mentioned, prohibits grounding the neutral conductor at more than one point in a multi-phase system. The primary reason behind this regulation is to prevent the creation of parallel neutral paths. When the neutral is grounded at multiple locations, any voltage differences between those ground points can cause current to circulate through the neutral conductors and the grounding system. This circulating current can lead to increased conductor heating, voltage drops, and electromagnetic interference. Furthermore, it can make it difficult to accurately measure ground fault currents, potentially delaying the operation of protective devices. To comply with NEC Section 450.14g, it is essential to establish a single, well-defined grounding point for the neutral conductor. This is typically achieved by connecting the neutral to the grounding electrode system at the service entrance or at the source of a separately derived system, such as a transformer. By limiting the neutral grounding to a single point, the risk of circulating currents is minimized and the integrity of the electrical system is maintained. NEC Section 250.24d requires the use of separate neutral and grounding conductors in all wiring systems. This separation is critical for ensuring that fault currents have a dedicated path back to the source, minimizing the risk of electrical shock. When the neutral and grounding conductors are combined, a ground fault can cause the entire grounding system to become energized, posing a significant safety hazard. By keeping the neutral and grounding conductors separate, a low impedance path is provided for fault currents, allowing protective devices to quickly clear the fault and prevent injury or damage. In addition to safety benefits, separate neutral and grounding conductors also reduce the risk of electromagnetic interference. When the neutral and grounding conductors are combined, any current flowing through the neutral can induce a voltage in the grounding system, creating noise that can disrupt sensitive electronic equipment. By keeping the neutral and grounding conductors separate, this noise is minimized and the performance of electronic devices is improved. NEC Section 250.26 further reinforces the importance of single-point grounding by prohibiting the bonding of neutral and grounding conductors at more than one location within a building or structure. This regulation is intended to prevent the creation of ground loops, which can cause a variety of problems. As previously mentioned, ground loops occur when there are multiple paths for current to flow to ground, creating a closed circuit. These loops can act as antennas, picking up electromagnetic interference and injecting noise into the electrical system. This noise can disrupt the operation of sensitive electronic equipment, leading to malfunctions and inaccurate readings. Furthermore, ground loops can create a pathway for stray currents to flow, increasing the risk of electrical shock and potentially damaging equipment. To prevent ground loops, it is essential to ensure that the neutral and grounding conductors are only bonded together at a single point, typically at the service entrance or at the source of a separately derived system. By limiting the bonding to a single point, the creation of multiple ground paths is avoided, and the risk of ground loops is minimized. In addition to the code requirements, it is also important to consider the practical implications of multiple neutral bonding points. One of the most significant concerns is the potential for unbalanced current flow. In a three-phase system, the neutral conductor is intended to carry only the imbalanced current, which is the difference between the currents in the three-phase conductors. However, when the neutral is grounded at multiple locations, current can flow through the neutral conductor even when the system is perfectly balanced. This is because the multiple ground paths create parallel circuits, and current will flow through each path in inverse proportion to its impedance. As a result, the neutral conductor can become overloaded, leading to increased conductor heating, voltage drops, and potentially even insulation damage. To prevent unbalanced current flow, it is essential to ensure that the neutral conductor is properly sized and that it is not grounded at multiple locations. The neutral conductor should be sized to carry the maximum anticipated unbalanced current, and it should be connected to the grounding electrode system at a single point. Another practical consideration is the impact of multiple neutral bonding points on the performance of sensitive electronic equipment. As previously mentioned, ground loops can create a pathway for stray currents to flow, which can inject noise into the electrical system. This noise can disrupt the operation of electronic devices, leading to malfunctions and inaccurate readings. In particular, sensitive equipment such as computers, programmable logic controllers, and medical devices are particularly vulnerable to noise-related problems. To minimize the impact of noise on electronic equipment, it is essential to ensure that the grounding system is properly designed and installed. This includes using separate neutral and grounding conductors, limiting the neutral grounding to a single point, and providing adequate shielding for sensitive equipment. Furthermore, it is important to use high-quality power conditioning equipment to filter out noise and voltage fluctuations. In addition to the technical considerations, it is also important to consider the legal and liability implications of multiple neutral bonding points. As previously mentioned, the NEC prohibits grounding the neutral conductor at more than one point in a multiphase system. Violating this code can result in fines, penalties, and even legal action. Furthermore, if someone is injured or property is damaged as a result of a code violation, the responsible party may be held liable for damages. To protect against legal and liability risks, it is essential to ensure that all electrical work is performed in accordance with the NEC and other applicable codes and standards. This includes using qualified and licensed electricians, obtaining necessary permits, and conducting thorough inspections. In conclusion, a practice of bonding the grounded conductors of multiple transformers together at multiple points is a violation of NEC rules and poses a safety hazard. It is recommended that the C-rated transformers be replaced with UL-certified transformers and that the neutral and grounding conductors be separated. By following these recommendations, you can ensure a safe, reliable, and code-compliant electrical system. The importance of UL certification cannot be overstated. UL-certified transformers undergo rigorous testing to ensure they meet stringent safety and performance standards. This testing covers a wide range of potential hazards, including overcurrent, overvoltage, insulation breakdown, and fire resistance. By using UL-certified transformers, you can have confidence that the equipment has been thoroughly evaluated and meets the necessary safety requirements. In contrast, transformers that are not UL certified may not have been subjected to the same level of testing, and their safety and performance may be questionable. This can increase the risk of electrical hazards, equipment damage, and personal injury. Therefore, it is always recommended to use UL certified transformers whenever possible. When selecting UL certified transformers, it is important to choose the appropriate type for the application. Transformers are available in a variety of sizes, voltage ratings, and configurations. It is essential to select the transformer that is properly sized to handle the load and that is compatible with the existing electrical system. Furthermore, it is important to consider the environmental conditions in which the transformer will be installed. Some transformers are designed for indoor use only, while others are suitable for outdoor applications. It is also important to consider the operating temperature, humidity, and altitude. By carefully considering these factors, you can select a transformer that will provide reliable and safe performance for many years to come. In addition to UL certification, it is also important to ensure that the transformer is properly installed and maintained. Transformers should be installed by qualified and licensed electricians in accordance with the NEC and other applicable codes and standards. The installation should include proper grounding, overcurrent protection, and ventilation. Furthermore, transformers should be regularly inspected and maintained to ensure that they are operating safely and efficiently. This includes checking the insulation, connections, and cooling system. By following these recommendations, you can extend the life of the transformer and prevent costly repairs. In summary, replacing CE-rated transformers with UL-certified units and separating the neutral and grounding conductors is a critical step in ensuring a safe, reliable, and code-compliant electrical system. By following these recommendations, you can minimize the risk of electrical hazards, equipment damage, and personal injury.